But the plan for today is okay. I introduced this ultra filter gadget last time, and this lecture is the promised payoff of that, where I make something cool with it. Um, and so, if I outline the plan for today, what we're going to do is we're going to take an indexed family of structures, and so suppose they're sort of indexed by natural numbers, M1, M2, M3, and maybe there's infinitely many of them. And I said structures, and I guess for continuity with the seminar so far, we have been saying interpretations. I guess I'm going with structures because it's sort of adhering to the notes that I'm deriving my notes from. And also, I will also be using I as the symbol for the index set. So please tell me to re-explain notation if it's not clear what something is. But yeah, structure is just an interpretation, so a domain and sort of ways to interpret the terms in a given first order language. And so what we're going to do is, in order to make the promised non-standard model, in general we can take an I-indexed family of structures, and we're going to make a new structure which in a way projects into all of these structures. So the objects are kind of like an index sequence of objects. So if you take an object from structure 1, one from structure 2, one from structure 3, and so on. And the this won't work on its own. What we need to do is we need to quotient this thing, like put some kind of equivalence relation on these things, using the ultrafilter, and then we're going to characterize truth in the sort of big model we've created out of all of these smaller structures. We're going to characterize truth in that structure by kind of like in a vague way, like being true in most of the structures, where most is sort of according to the ultrafilter. And then once we've done that, I'm going to show you the sort of the set of natural numbers case, and we'll talk about the hypernaturals. And so, well, the easiest path there is to kind of just skip to the end, and then we and do it sort of informally, and then I'll show you the formal way to do it. But hopefully this will give you a picture to have in your head as we go. So I'm going to informally tell you about the hypernaturals. And so just like the picture above, in this example, so this is the sort of non-standard model I'm going to make. It's going to be called star n. And the kind of things that are in star n, well, the point of it is that it's supposed to be a model of arithmetic. And so, in particular, in the language of arithmetic, you have numerals, which are like there's 0, and there's the successor of 0, and the successor of the successor of 0, and so on. And those are your numerals. Not one. That you have the numeral 0 there. Will, can you remind me? When we write a numeral, is the line over it or below it?
Oh, it's below it.
Okay, so this is the numeral 0, means that symbol above, and then numeral 1 is S open bracket 0 close bracket, and that's 2, and so on. And so in order for this to be a model, okay, what is the object? What is the hypernatural object, which those numerals are interpreted as? Well, for example, 2 is going to be it's going to be something like this. It's just kind of a constant sequence of 2s. That's a canonical representation for the hypernatural 2. But the whole point of the ultrafilter is to now identify this with any other hypernatural which is mostly the same as this hypernatural. So, for example, this is equivalent to, say, let me just replace finitely many of the numbers in this sequence. So say I just replaced a couple of those, and then from then on, it's all just 2s. So the idea here is that, yeah, as I said, only finitely many of these things aren't the same as the corresponding position. Well, I guess I'll point out the ones that aren't the same. It's this one, and I guess past that, it doesn't line up anymore. Yeah, in those positions, they disagree, but in cofinitely many positions, they're exactly the same. And so that's the equivalence relation on the hypernaturals. Is you take your ultrafilter and, like, on the indexing set, in this case, the indexing set is also just the natural numbers, and you use it to identify hypernaturals which are mostly the same. So there's a standard hypernatural, which is just it's just an interpretation of one of the terms of the language. But the whole point is now we have these extra exotic things which are not equal to, like, an interpretation of some numeral. So the most obvious weird one I can come up with would be this number I'll call k, which is just 0, 1, 2, 3, 4, 5, 6, and so on. And so clearly this is not equal to any, like, standard hypernatural, because it's if you take any of these of the sort of numeral hypernaturals, or like anything it's equal to, and compare, like, pairwise, the equality between the sort of normal naturals in the sequence, you will only have I guess finitely many, or like a co-large amount of agreements between them. And so this is a truly exotic hypernatural. Someone's got their microphone unmuted. I think it's you, Dan. He might not be at his computer. Okay, I'll just proceed. Okay, any questions about this already?
Not at the moment.
Okay, great. So just to I've shown you how to interpret, like, some numerals and maybe some one of the weird objects. Let me show you how addition works. So it works sort of point-wise. So if I write out k plus 2, all I have to do is add them up in the corresponding position. So this would be 2, 3, 4, 5, 6, 7, and so on. And so the question you should ask is, if I swapped out for, like, a hypernatural representation like this one that was equal to the first one and then did the addition, do I end up with an equivalent thing? And yes, you do. So in this case, if I say use this thing to add to my number k instead of the other one, I'd end up with 2, 4, 4, 5, 9, 105, and then it would just proceed 8, 9, 10 as normal, and so on. And so again, it's only co-finitely many positions of this infinite sequence in which these two representations of this hypernatural are different. So that makes them the same hypernatural. So beyond that, there's like, here's some examples where I can't say. Okay, let me try these two numbers. So one of them I'll call A, which is just 2, 3, 2, 3, 2, 3, and so on. And the other one is 3, 2, 3, 2, 3, 2, and so on. And the kicker here is I don't know which of A and B is even or odd, but I know that exactly one of them is. Because if I okay, yeah, I was talking about equality between objects, but as I was saying before, truth of hypernaturals is about truth at most of the sort of substructures, and you can see exactly half the time in this hypernatural A, you get an even number, but it's at all of the even positions in the sequence, and it's odd in all the odd positions of the sequence. And so the question of whether or not A is an even number is going to is an even hypernatural is going to boil down to whether it's going to boil down to which sequence, which set in your ultrafilter you designated to be large. Is it the set of even numbers is large, or the set of odd numbers is large? Because those are the sort of indices that correspond to evenness or oddness in these numbers. Any quick questions about that before we get into the formal stuff?
I don't fully understand the last point, but I think I just want to see the formal stuff, and I think it will
Okay.
start clicking. So I think you can just move on.
Okay, I think part of the confusion is probably because there's two, like, evenness and oddness shows up in two different ways in both the members of the sequence and the indices behind the sequence, but maybe that every third number will even and the rest are odd, or the yeah. So again, that will entirely depend on it'll depend on the ultrafilter, which in some sense, for particular sets, especially the infinite ones, it will be kind of impossible to answer that question in general, because, as I said, it'll depend on the ultrafilter. But because every ultrafilter contains the cofinite filter, we can still sort of there's enough like for the questions which can be answered by, oh, the cofinite set is in the ultrafilter, we'll be able to grasp those things about the model. Okay, let's press on. Okay, so definition 201. So we take some I-indexed collection of L structures. So L is our first order language. And then we take an ultrafilter. So this is my calligraphy U. Okay, now we're defining the ultra product. The ultra product is written like this, it's written as a product over I of all the mi's, and then we're quotienting. Well, there's just the notation. What does quotient by the ultrafilter mean? That's what I'm going to define. So first I have to tell you what the domain is. So like the underlying set. And it's just the normal set product. And I guess, so I will freely abuse notation here by identifying the model mi with the domain of the model. Like there's extra stuff that's in the model that's not part of the domain, as in interpretations of other symbols. But I just mean the domain here. Quotiented by
Yeah, that's fine.
equivalence relation. Yeah. Where so I'll write like circular round braces with some index when I mean indexed by capital I, but I'll just omit that part of it. So two, I'm going to call them sequences, but like, I don't know, I could be uncountable if you wanted it to be. So we identify two sequences if and only if they agree on a large set. And what I mean by that is this set such that AI is BI. That set, that kind of pre-image in a way, is in the ultrafilter U. And so, for example, on the last board, I was identifying two different representations of 2 by saying, well, I changed. We start with the entire okay, this set that I've written down here in that example in the previous board where I identify the two versions of 2 of the hypernatural 2. The set of indexes such that they're equal is cofinite because only finitely many of occurrences aren't equal. And as I proved last time, every ultrafilter contains the cofinite filter, meaning it has all the cofinite sets. So although I know nothing else about the ultrafilter, I still know that you always identify two sequences if they're only cofinitely different. Okay, so next up, I need to tell you how to interpret the constants, function symbols, and relation symbols. So if C is a constant symbol, okay, this again, I'm sort of using the notation of the notes I got this from, but we will probably write it a bit differently in previous seminars. So when you put the model as the superscript, that's the interpretation of this symbol in this structure. And so the interpretation of C is you interpret C in all of the MIs, and you make an I sequence out of that. And then you take the equivalence class of all of those the equivalence class of sequences which are equivalent under this relation to that sequence. So, for example, when you take the constant symbol 0, I'll write this in a different color. You interpret 0 in the hypernatural structure as before. you end up with, actually I should write star n is equal to this thing, because it's just interpreted as 0 in every single structure. I'll point out that here in the general case, I'm allowing each structure mi to be a completely different structure. But the example we'll be interested in for hypernaturals. So yeah, in the hypernatural case, all of the structures are just the same one. That ends up being called an ultra power for obvious reasons. Okay, now to interpret a function symbol. So if f is a function symbol, of arity n, then can I fit this here? I'll go to the next line. F m, so the function that the function symbol f is interpreted as in this structure m is the one which takes n of these objects. So I'm going to write it like this: ai1 dot dot dot. And let me close that equivalence class up to ain. These i's don't have anything to do with each other. That's just sort of, that's a sequence inside itself. If you apply a function to those objects, you end up with the object which is pairwise apply. We're making a sequence of things, and each of those is going to be, we'll interpret f in the structure mi and apply it to the object ai1 up to ain. And here the i's are linked. So it's like this is one, I'm making one sequence of things here, and I'm fixing I across all of these AIs, applying the ith interpretation of f amongst the structures to it, and I make a sequence out of that, and then I take the equivalence class of all of them. So the canonical example of this is what I did on the previous board with adding k and 2, is I'm sort of pairwise, I'm interpreting the function symbol plus as the regular plus in the standard model of natural numbers, where you just add up the numbers as normal. And then, applying that pairwise to each element of the sequence, and then taking the equivalence class of the resulting thing I end up with. Is that clear? I hope so.
Wait, I think so, but I don't understand the notation. But I feel like I'm just not getting it. So this AI1 is a sequence, and then you're taking an equivalence class of that sequence, which is fine.
Mm-hmm.
So you've got a finite sequence of equivalence classes of sequences, and then you're taking a representative of each of these equivalence classes. So you've got n sequences in your hand, and then how do you form AI1 up to AIN
So
from n sequences?
You fix I, and then you go to each of those sequences and pick the ith element of each sequence, and you pull that one
That
out.
doesn't make sense. So the ith element of the sequence, so AI1 is a sequence.
So
AI1,
there's
AI2,
maybe I
AI3.
would write it like this. I'm just trying to avoid too much notation, but maybe that's hurting it. AI1. If I write it with brackets like that, that's a sequence where, like it's I'm just neglecting to write this, to write I in I. So in this, when I write this notation,
Oh,
I is not a free variable there.
okay. So AIJ
Yeah.
is the ith element of sequence J.
AIJ.
Is the ith element of
Yeah.
sequence J.
Yeah,
Yeah, okay,
when
that
it
makes
appears
sense.
here. But the I's as they appear here, they're a captured variable that I'm just not writing the extra bit here for. I can write
Okay, I see.
this here.
Yeah.
Does that make sense?
Yeah, that's fine.
Cool. Okay. Now relations. R is a relation symbol of arity n, then the interpretation of R in this big model is same as before. That's equal to 1, like the truth value 1, if and only if similar thing to the equality thing. So the set of all indices such that when you look at the ith structure and interpret R, and then apply that to the ith term or the ith object of all the sequences, that's equal to 1 a large amount of the time. So that's how I determined that. I guess so. If this set, if we were talking about the evenness of A from the previous board, if you apply the sort of evenness predicate, well, I guess this is strictly about relation symbols, but it's going to work similarly for like any formula. When you apply the evenness predicate, you look at this set of indices where you have where like the predicate holds of the element of the sequence within the ith structure. When you construct the set of all those indices, if you end up with a large set according to the ultrafilter, then that ends up being that means truth. That means it's true in this model.
Well, that makes sense. So that's what you were saying earlier, that whether 232323 is even or odd depends on the choice of ultrafilter.
Yeah. Yeah.
Okay.
But if you end up with a cofinite set as the sort of amount of sets where you have where your predicate or your formula is true in each of the ith structures, then there's no question of which ultrafilter you're using, because
Yeah.
the any cofinite set is guaranteed to be in the ultrafilter.
Yeah, makes sense.
Okay, cool. New board, making progress. Okay, so in the notes I was following, and in this lecture, it's left as an exercise to show that the equivalence relation, or that, show that defines an equivalence relation. and that the interpretations of terms and relation symbols is well defined. So this is just talking about that when we define the interpretation, we were sort of taking a representative amongst the equivalence class of sequences. So it's fairly straightforward to verify that, but I won't be doing that now. So the theorem is this is I meant to look up the translation again. Sorry, not the pronunciation, but I believe it's Wash's theorem. I'm going to say it like that. Spelt with a fancy L, an O, and then a S with an accent. And then I believe
That's what I would have said, but it means absolutely nothing. That's what I would have said.
I think there's an apostrophe. I get because it's an S, like it's an
Oh
S.
man, that's so confusing. I got no idea.
Wash's theorem, right?
I don't know. Is that an S?
Yeah, I'm going to say it's an S. Okay, so cool. I'm going to write this theorem, which is essentially lifting the relation symbol definition to a theorem about any formula. And what's going to happen is I'm going to write something that's actually nonsense, and then I'm going to say why it's nonsense, and then we're going to fix it. So look out for that. So actually, I won't write this. I was just going to write let Mi be a I-indexed family of L structures, where L is your first order language, and then again U an ultrafilter on I. So that's the same as in our previous definition. So with that out of the way, let phi of x bar, which is just again notation for like a tuple of things, and this is in this case it's a tuple of variables. I'm just using the notation from the notes, and then I'll give my sort of modifications for it after. Let phi of x be a first order formula in the free variables x bar, and let AI bracket bar be a tuple of objects from the ultra product. So let me write that. So here, again, I is a captured variable. It's just about the sequence AI inside this thing, and the bar is denoting a tuple, a finite tuple of things. So the I has nothing to do with the tuple. So let that be tuple of objects from the ultra product.
Wait, so you've got two different notations for tuples inside the same thing. Like there's a sequence AI, and then you're taking a tuple of equivalence classes of sequences, which you're notating with a bar.
Yeah.
Is it a finite tuple, or can it be arbitrary? So it's necessarily finite.
One.
Okay.
Yeah, I didn't sort of try and massage this notation too much because I end up writing it differently in the next bit. Let me just get through this. So mi quotient u. So some tuple of objects from that ultra product. So I could have just said like I could have just listed them out and instead of saying tuple of objects, but whatever. All right, here's the theorem. So this ultra product entails this thing, or in other words, this is true in this structure. If and only if this set of all indices such that this formula is true in the structure Mi is in the ultrafilter. So again, just compare this with the definition of the relation symbol. So all it's doing is just lifting that to like take any formula. But okay, here's the problem. I mean, can anyone point it out yet as to what's sort of nonsense about this?
I mean, there's a check on the equivalence class, but I feel like that's not it.
No. So the problem is that let me put it in red. This is not a formula. Like this is not necessarily. This part is kind of nonsense, and so is this part, because these things are not like symbols. Like I'm supposed to, when I say a structure or an interpretation makes this formula true or entails this formula, it's supposed to be a formula. But what I've done is I've like sort of started with my language. I've said, all right, here's some structures with domains which like interpret theories or interpret formulas over that language. And here's some objects like in the domain of those structures. And then I'm using those objects as if they're already part of the language, but they're not. So it's strictly they're not they're not formulas. So like unless you already believe in some kind of sort of mixing together of your like meta theory and theory, I think this is sort of in bad taste, and there's a sort of more correct way to communicate this idea that kind of properly like describes the kind of spirit of doing first order logic.
Yeah, I see your point, but you can just replace the thing on the interior with a constant symbol or something, and then interpret that constant symbol as this particular object, right? Like that's the intention behind this notation.
Right, but so I was going to list like two options. One in which when you state Walsh's theorem, you first like you take your index family of structures and then you like add an absurd amount of like constants, each to name every single object.
Mm-hmm.
And then I can actually write this and it actually makes I guess it sort of counts. Um or I guess you were saying like uh on a case by case basis per object, like decide to
Mm-hmm.
or like I guess you augment the language once, put your constant symbol there, and say, all right, this time I'm going to because then this time I'm going to interpret the constant as this object. But I guess I don't know. That's a little unsatisfying because of the fact that like the point of Walsh's theorem is to characterize truth in this model. But if you're like
Mm-hmm.
switching out the model every time for like a slightly different one, I think that's less satisfying. And I think you can do something else to sort of facilitate that, which is my the second option I wrote down, which is just using valuations to do this, because it's kind of more in line with the canonical story of, all right, first order logic, you start with some countable, decidable collection of things that you're going to use as your symbols. You build theories out of some language where you name the things you need to name, and then you do semantics where, as the meta theory, you talk about how the syntax of first order logic and your first order theory, how it relates to the sort of real objects in your meta theory. So like you can't do semantics without the meta theory. So let the meta theory do its job rather than like just shove in like chunks of the meta theory into like the first order language. I think is a really gross way of doing things.
Yeah, I agree. Yeah, sure.
So let me restate it, which is, I think it's a cleaner way of doing things. So how you do it is you talk about valuations, which I haven't really done yet. So just to remind you, I'm going to take a valuation for each of the MIs. And I know in the notes it's a Greek letter nu, but I just can't bring my brain to recognize it as anything other than the letter V. So I'm just going to say V. So VI is a valuation which is a function from the set of variables to the domain of MI. So take that I indexed family of valuations. And then the whole valuation is the one which takes any variable into the domain of the ultra products. Which sends a variable x to, you just pairwise, well, not pairwise, index-wise, apply each valuation. And then you get a sequence indexed by I, and then you take the equivalence class of those sequences. So, okay, let me just continue and state the theorem. For any, what is it? L formula. Phi, we use var phi here, or curly phi, or whatever it's called. And then in the notation we've been using in the seminars, you sort of subscript with the valuation. So interpretation in this structure with valuation V of this formula is 1 if and only if, again, MI with valuation VI. Sorry for all the subscripts. Of phi is 1. If the set of all those i's is a large set. So here you're letting the meta theory do its job in relating meta theory objects to your formula. And yeah, the idea is you want to say the formula about the objects, and you're letting the meta theory do it by whenever a variable shows up in phi, the valuation vi gets applied to it. Yeah. Okay. So that's my restatement of it. We can talk about it more later, but I need to press on for now. So join me up here. Okay. So the proof is by induction here. Let me try and do it as timely manner as I can. So proof. By induction on the formula. So in our base case, yeah, I'll write it out. So I won't write out the surrounding text. I'll just write down the meat of it. So if you've got an atomic formula that's just relation symbol with a bunch of terms, and you apply MV of that formula, that thing is 1 if and only if interpretation of I applied to all the objects yields 1. That's just normal first order logic definition. And then by the definition of the model, we can exchange this with a set being large. So the ith model mi of R applied to the ith model mi with vi of T1. And the same thing with Tn. Set of all i's such that that's equal to 1 is large. And that's by, the definition from before. But this is just exactly what it means to say, I'm just rewriting inside the set here. That's just the interpretation of this formula in the ith model. And that's exactly what we want for that inductive case. I won't do the equality because it's a bit too similar to the previous one, but the next one is kind of a critical moment. So let me just excuse that case. Okay. Now, if phi is a negation, then we have not psi is true in the ultra product with the valuation v, if and only if phi is false. But that, by definition, or by the inductive hypothesis, means it's not the case that this set is large, meaning it's small. Mi vi of psi. So the set of models at which the projected object has the property psi, I guess, is not in the ultrafilter. But that's the same thing as If that's not in the ultrafilter, then the complement is in the ultrafilter. This is where we use the ultrafilter axiom. So not equal to 1, i.e. equal to 0. So this set must be in the ultrafilter by the ultrafilter condition. And then that's the same as MIVI of not psi equal to 1. Wait. Oh, yeah. In the ultrafilter. And that's exactly what we wanted. Did you follow that?
I imagined that's exactly where you're going to use the ultrafilter axiom. So it makes total sense.
No surprises. Negation is complement. The next one. Okay. Next one is where we'll you can make an equally educated guess as to what we will do with conjunction. So the truth of psi and theta that means that psi is true and theta is also true, and that's the case. Is by the inductive hypothesis that the associated index sets that I've written analogous versions of already is large, and I'll just sort of skip ahead to I'll just write it out. MIVI psi equals 1 is in U, and my iPad is so hot. It's like I'm writing on a barbecue.
Yeah, mine did that every time I shoot as well.
Actually, I probably should turn down the quality. Hadn't actually done that. All right, thanks.
No, I just burned my hand instead.
Yeah, so both those sets are large, and okay, I can explain both of these directions of this upcoming equivalence. It's the same as the intersection being in the ultrafilter. And so the forward direction is just applying the intersection axiom for filters. If you have two large sets, you take their intersection, you end up with a large set. And then the other direction is the superset axiom. So if the intersection is in the filter, then the two sets that you intersected, they're both supersets of that intersection. So they're also large. They're also in the filter. Okay, and then you just proceed. You squash those two sets together, and I'll just skip to this part where it's MIVI psi and theta equals 1. And again, that's exactly what we need. Okay, there's a case for exists x psi. I will skip it because there's some it takes some thinking, but I don't think anything interesting really happens. There's not much ultrafilter interaction. Yeah. All right, so I'll skip that one and try and end on some more interesting notes. But then after I do the I have to walk my iPad character over closer to the board because it rendered out. After I do this case, then I claim the cases for disjunction, implication, and universal quantification can be obtained by equivalences to formulas using only the previous connectives. And that's the proof by induction. Any questions about that?
Well, makes sense.
I guess maybe the question to ask is, do you believe it that that this is, maybe you don't have a solid sense of it, but that truth in this model is indeed characterized by truth at most of the projection models?
Yeah, as long as we understand most to be large, as in set inside an ultrafilter. I'm still not sure how I feel about the intersection property, but modulo that, I believe it.
Yeah. So, yeah, as I said last time, like large kind of like becomes weirdly opinionated at the sort of infinite sets, which are not cofinite territory, but uh, it makes sense for the finite and cofinite sets, and that's where we will be sort of making all of our general claims about any ultra product.
Okay.
Okay, so a corollary of this, I'm going to try and make it specialize that theorem to make it a bit more palatable.
Did the orb cam move? Or is it still over the other two boards?
Now it's moved. So a corollary is, all right, let me grab my notes. So let's go super specialized. Let L be the language of arithmetic. And so star n, this is our hypernaturals model, is this ultra power. So I'm going to write it with like a sort of superscript power notation. So it's n to the power of n, quotiented by the ultrafilter, which written in the ultra product notation is just the product over all natural i's of just a bunch of copies of the natural numbers, quotiented by ultrafilter. So that's an ultra power of n. I was going to say ultra power of n copies of n, but it's just an ultra power of n consisting of n copies of n, I guess, quotiented. And that's for some ultrafilter U. And these are called the hypernaturals. So you can obviously criticize the usage of the there because it's sort of dependent on which ultrafilter you pick. But again, we can still say things about we can still make cofinite sort of statements about hypernaturals that are true regardless of what ultrafilter you take. And then, so again, for any valuation v, which sends variables to things in to hypernaturals, which splits into VIs for each of the copies of n. And any formula phi, you have truth in this model with that valuation of phi, if and only if large set, as in true in most of the models n. And so because like you've got a different valuation vi in each depending on I, you might get a different you might be talking about a different natural number at each model, even though they're just copies of the same model. And I said that has to be a large set. So I want to now talk about some examples of hypernaturals, and we can I'm sort of returning to what I was saying at the start. We're going to say some interesting things about them. Okay, so I was going to write, so each numeral, I won't write this. Each numeral in the language corresponds to like the equivalence class of sequences, and the representative is just you take it's just the constant sequence of that normal number. So maybe I should just write it. When you interpret with any valuation, the numeral n, so maybe I'll write it like this. And there's n s's. That thing is this equivalence class of sequences which are equivalent to just this constant sequence. So that's your standard hypernaturals. And then, as I mentioned before, there's K, which is just the sequence of all the natural numbers in order. That thing is larger than any standard hypernatural. And so this is the point at which, like, you can clearly see that, like, okay, obviously when you have like sequences, just sequences of copies of n, you get way more elements than like just your countable standard model of n. But maybe when you take the quotient by the ultrafilter, like, all of that weirdness goes away and you kind of just get an isomorphic thing back again. This is your sort of first indication that, like, there is genuinely way more stuff here and way more weird stuff that's not like the natural numbers in a certain way. So let me prove what I just said. It's just the observation that the set indices such that I guess this is sort of bad notation, but let's say k is sort of identified with that representation I wrote down. Or maybe I shouldn't say the representation. I should just say such that I is greater than n, which is the standard hypernatural projection here. That set is equal to, say, n plus 1, n plus 2, and so on. Which is cofinite. So I have a object in my interpretation of I have an object in my structure which is larger than all the things named by a numeral in the language of arithmetic. And so when you do things with the compactness theorem, where you force there to be more objects. Sorry, I guess what I mean sort of more in the spirit of the Lowenheim-Skolem theorem, where you force there to be more objects by sort of introducing a constant, a new constant, and saying it's not equal to all the other like named natural numbers. Or if you do that, this could be the sort of new object you have in mind. This is a number that's this is an object in the model which is not equal to any of the named objects. And it's also larger than all of those things. Any questions about that example? I've got some more. But
So no matter what you interpret 0 as, there's no number of times that you can apply the successor to it to get this object k. That's the point, right?
So it's not equal to any of the, because applying the successor just means like you just get one of these standard hypernaturals, but it's never equal to this because you always have a cofinite amount of places where it's not equal.
Here's a dumb question.
Let me continue on and do some more ones.
Couldn't you just say from the beginning that actually my axioms for the natural numbers are that everything is a successor of 0 or a successor of
so that's a key point, is like kind of the whole, like a large point here is that it's not possible to do that. As in, okay, maybe you decide that you can do that in your formalism, but because of what I've done,
I need to talk about. Why can't I say that?
Because then what you're doing is not a first order thing. You will end up violating the compactness theorem, and therefore it will not be possible to write down a logic and a semantics such that you have soundness and completeness. So it's all a game with respect to that. So like we would really like to, like, okay, maybe, so of course maybe like whatever, there's no rules. You can say everything is the successor of some, as a finite amount of successors of 0. But yeah, then you're not playing the first order game anymore. So
how rude.
Yeah. Pardon?
I said how rude.
Yeah, so I guess a core point I want to get to is well, with any of these seminars, is kind of on first order logic, is what can you fit into first order logic? Like, plainly, what are the sort of limits of first order logic in what you can get it to do? And what you just said, sort of making the first order theory of arithmetic is not categorical is the way to say that, because it's exactly this, in that there's no way to follow all the first order rules such that you end up with only one model of arithmetic up to isomorphism. Actually, I've got some cool more hypernaturals, but let me just state the sort of theorem that kind of blew my mind and made me want to talk about this. Is I guess I see this sort of next to the incompleteness theorem as sort of an implication of that something. It sort of contradicts something that I thought was kind of implied in the incompleteness theorem, which is, let me talk about. All right, let me just write a theorem and go back into boring details mode. One moment. Okay, so theorem 2.0.6. For every first order formula phi in the language of arithmetic, star n, oh no, just n entails phi if and only if star n entails phi. This is just sort of it's the same as the previous theorem, but I'm just the premise in both directions is that, well, this entails symbol is just saying for any valuation. So pick any valuation you like. The premise is that the formula is true with that valuation in this model. And then you apply the previous theorem to get the same fact about truth in this model for any valuation. So there's some details in figuring that out. And then you can also do the same thing in the other direction. And so a corollary of this, I'll come back to maybe make you not want to believe the corollary, and then you can scrutinize the theorem. Corollary of this, this is the weird thing. Star n is a model of this set, the theorems of n, which is the set of all phi such that n entails phi, which is also called true arithmetic. So let me rewind for a second. I guess what Will was thinking about with the incompleteness theorem is, okay, let me remind myself. The point of it was, okay, we really want to axiomatize piano arithmetic, and the point was we cannot make a complete theory of arithmetic if we restrict ourselves to computable axioms. So if the axioms of the theory are computable, then there is no way to make it such that we can prove all of the formulas in this set. Do you agree with that, Will? Does that make sense?
Yeah, that's what I was saying.
So in that characterization, sort of this set was kind of like the holy grail. It's like, okay, we really want to be able to prove all the things that are true about n, because that's what n is all about, right? it's true arithmetic, but we can only ever achieve with computable axioms the sort of like a part of true arithmetic. And so in my mind, this made true arithmetic the holy grail. It's really the like, this is the thing to achieve. But this theorem here is saying like, well, actually, like, even if you got there, it's like you haven't categorized the models of arithmetic. You've got all the like the whole thing about non-standard models is not about like non-standard models don't go away even if you allow yourself to have uncomputable axioms. You can have all the axioms you want. It's first order logic itself, as in the restriction to only reasoning in a first order way, where you can apply selected predicates to like quantifications over objects. That is a limitation in itself in actually categorizing the models of arithmetic.
But why should I be offended by that? What's wrong with star n being a model of the theorems of n?
Because, well, it has uncountably many objects. I don't know. Is that enough for you or not?
No, not really, because couldn't I make lots of uncountable things models of the natural numbers? Like, it doesn't. Where's the surjectivity requirement, right? I mean, like, I can just interpret first order arithmetic inside the reals or something.
Yeah. So when you say interpret the natural numbers as blah blah blah, I think in your head you're already assuming interpret the piano axioms, as in like because clearly they like say a limited number of things. So like and yeah, so they say a limited number of things about the actual natural numbers, but like if we're talking about like, okay, the real natural numbers that maybe we don't know like until this theorem whether or not you can sort of say all the things about it to identify it with first order formulas, but the real natural numbers themselves, like that model, the point is there's no way to sort of to categorize just that with first order formulas.
Yeah, I see what you mean.
So what about induction? So would it be, maybe I'm off track here, but so is it true then in this non-standard model that if you can prove a proposition for 0 and that Pn implies Pn plus 1, then it's true for everything, even though not everything is of the form successor of successor of successor of 0?
Yep.
That's crazy. Yep. Crazy.
Yeah. So
that's insane. That can't. Yeah, I don't believe it.
Okay, so it's because there's no like you to imply, like you want to imply the induction axiom to like the formula which says like is the successor of something. But hang on. Yeah, the point is you don't get anywhere. I think like maybe a different non-standard model is like, I don't know it super well, but you kind of just have all the natural numbers and so on. And then way out at infinity, you just like chuck in another object A. And I think you can set it up so that you have A and B, where B is the successor of A and A is the successor of B. And so everything is the successor of something, because all you can hope to, like you want to say for all X, like you want to say like X equals 0 or exists Y is equal to the successor of 0. Wait, not 0, of X. Sorry?
X is equal to the successor of Y.
Yeah. But you can see that gets you nowhere, because like A is the successor of B, and B is the successor of A. Like there's no, like you're the only thing you can hope to do is sort of quantify over like a number of successors applied to like X. Or to 0 or something, and you can't express that in first order logic. And this is exactly where the incompleteness theorem, where like let me remind myself, you've got this formula which says of itself that it isn't provable, and you can't prove that because there is a model in which there supposedly is a proof that it's not provable. And what actually happens in that model is when you're talking about coding encodings, like Gödel encodings of formulas, and you have some kind of axiom or some formula that sort of asserts like the sort of like this is a proof tree that has these formulas as the premises and this formula as the conclusion, and all the deductions are like valid along the way. That formula is expressed by like talking about numbers, but there's nowhere to say, hey, when I say for all X, or when I say exists X, I just want to be talking about the numerals, the sort of named numbers. There's no way to do that. Like every time that, like in the non-standard model case, there's always the non-standard model case where like you could interpret your numbers in a weird way so that like you have these infinite numbers that, I don't know, maybe they sort of correspond to some infinite proof or something, or like it's just the weird numbers that have this weird successor relationship between them. They mess up the game, and they allow you to have they allow it to be true that this formula says that there's a proof that there's no proof of G, and there actually is no proof because the actual proofs are sort of correspond to like the actual encodings.
The neurals, yeah. Wow, that's fascinating. So, yeah. So,
Awesome.
why do people do first order logic? Why not go into second order logic where you can make these statements of like, and that's all that there is?
Yeah, and then goodbye completeness. That's basically why.
Why do we need completeness so badly?
If we don't have completeness, we're not touching the transcendental, man. We're like puny beings pushing symbols around.
No, but like we have soundness. So every time we do that, it still reflects truth. It's just we don't have the other statement. Everything that is true in all models is provable. So there might be like things that are true out there that we can't prove.
Yeah. Well,
but at least we can only restrict ourselves to the. Yeah.
So what completeness gives you that if you have a consistent theory, then there is a model. That's the sort of statement of completeness that sort of is in line with what Dan was just saying. And like completeness is the sort of
that sounds
is the sort of formalist is the only hope for like formalism, where like formalism is just like, oh, I'm just pushing symbols around, but like and the sort of justification for doing your formalism is, well, I know this set of sentences is consistent, or at least I think it is. And completeness then sort of justifies that by saying, well, if you have syntactic consistency, then there is a model that actually
yeah, but I still feel like that you don't have to be so attached to that. I mean, that kind of sounds like Hilbert's definition of existence or whatever, where if it is described in some consistent system, then it exists, right? You could abandon that and you could say consistency isn't sufficient for me to believe that we're talking about something. So I need to have a consistent system, and I need to prove that a model exists of that consistent system. And then whatever I do inside that formal system reflects truth inside at least one model.
Yeah, so I'll say that like the study of second order logic exists, so people still do it and talk about it. So that like I can't just say that like, okay, this it's not complete, so like there's nothing to say there. But like losing the different, like it's just that you lose completeness, and if you're interested in having completeness, then you don't get to leave first order logic in this sense.
Yeah. You see, because what I'm taking from this, like the non-standard models, the Gödel's Incompleteness Theorem, it feels like genuine flaws in first order logic, which can be described as you can't say the word only, right? It's like these are the only things in the model that I want to talk about. Like I have the numerals and I have the numerals only kind of thing. And that seems like this recurring thing that kind of blows our mind. Like we sit there and go like, wow, that's so mind-blowing, that's crazy, like blah, blah, blah. But it's because we don't realize that we have that restriction and we don't like swallow that. So once you've swallowed that and you're like, okay, we really want to be able to formalize that sentence, but we can't do that. So we need a system that can. And what that means is that we need to give up completeness. So that puts completeness under the spotlight. But then you realize, oh, maybe the deep realization is that consistency is not sufficient for realness, existence. A consistent system does not necessarily talk about any real phenomena. And that would seem to me like a reasonable philosophical take from this and Gödel's Incompleteness. That's my immediate reaction, at least. But yeah, I'll think about it. It's really interesting. This was a good choice of topic. Thanks for doing this.
No worries. Awesome. Can I show you like one or two more weird hypernaturals? So you have.
Unfortunately, I need to go. I need to run after something, but I can check the notes or the recording or something.
Okay. See you well. Thanks for coming.
All right. See you guys. Thanks.
Okay, so you've got the sequence of all the primes. That's also prime. It satisfies is prime. The sort of the first order statement is prime. And also because of what I just wrote, the n star is a model of true arithmetic. Star n also satisfies for all x there exists y is greater than x, and is y.
I see.
So this is a hypernatural prime, but there's also infinitely many hypernaturals which are larger than that prime and also prime.
That's crazy.
Then there's also this one. There's 2 times 3, 2 times 3 times 5. So this is Euclid's proof of the infinitude of primes in an object. It's this hypernatural is divisible by every standard hypernatural prime. So this is like it's the product of all standard hypernaturals, I guess you could say it like that.
This is pretty neat.
Yeah,
this has a very geometric flavor to me. So what is the spectrum of this thing? I mean, I can do Z, right?
Alright. So I don't actually know what a spectrum is. So
right. So you just take all the prime ideals of a ring. So if I take the hypernaturals and change it from a semi-monoid from a monoid into a ring by adding inverses. So I'll add negations. Then that's going to be a commutative ring, and the spectrum of a commutative ring is the set of all prime ideals. I don't know if this correspondence between prime ideals and primes still works. So if I say,
I mean, if you can go via this theorem here, then and do it all with the first order statement, then it will carry through.
yeah, but I mean, is there an operation of multiplication on the hypernaturals?
Yeah, it's just
the usual
pairwise.
Yeah. Okay.
I guess you can yeah. So this actually, let me just erase. I'll go to the next board. I don't know if this helps, but I said this was prime. And it's because take any product of two hypernaturals that is equal to this. So this is equal to this times something. So I'm saying it's prime. So I'm saying one of these things is P is this hypernatural prime, and one of them is the number 1. It's like equal to the numeral 1. And what you do is, okay, well maybe like it's either 2 1 or 1 2 there, and maybe 3's there, 1's there, maybe 1's there, 5's there, and then 1's there, 5's there. And so on. You make all these choices. Depending how you do it, well, you got 2 complementary indexing sets where, like, so either this one of these is equal to this numeral, and the other one is equal to 2 3 5 7, so on.
Yeah, I see.
So that's why that thing is prime. So I guess actually that didn't really lead into the point I wanted to make, but yeah. So the weirdness is I stated a lot of this sort of out loud, and even in the notes I kind of just said it informally, because the whole point is you can't sort of describe this relationship as in like this hypernatural is larger than all the standard hypernaturals. I can't say that like by talking about a first order formula, because I can't sort of with a first order formula say hypernatural or say standard hypernatural. That's kind of reiterating a point I already made. And so like the number k or this weird prime hypernatural is larger than every standard hypernatural, but it's not larger than all of them. So all the logic about the normal naturals, about like there's no number, there's no natural which is larger than all other naturals. That corresponds to there's no hypernatural which is larger than all hypernaturals. And so the weird, like you can only identify the weirdness from the meta theory, where you can sort of see these are the naturals, these are the standard hypernaturals, these are the weird hypernaturals.
Yeah, this is a very instructive example. I mean, the hypernaturals themselves, not this particular prime thing.
Yeah, so yeah, there's the hyperreals too. Just do the same thing, sequences of reals quotiented by some ultrafilter. And yeah, so the second reference in the notes is where I sort of really inspired me, because it's a really good overview. There's a sort of series of blog posts about it, and they go further in sort of talking about like they have a couple more examples. I stole these sort of prime examples, prime hypernatural examples from there. But yeah, you can also go on to prove the compactness theorem in a direct way. Like normally compactness theorem is like, all right, I can like it's sort of it's a proof by contradiction.
Mm-hmm.
And like you just sort of introduce a constant and then oh sorry, no, you don't do that. It just is a proof by contradiction, and then you have no sense of, all right, I've got all my models of all the finite subsets of my theory, but what's the model of the whole theory? That supposedly that's what compactness is about. Well, you can actually do it sort of in a more direct manner. You actually use each of the finite models to construct a model of the whole theory.
Mm.
So that blog post goes more into that.
Yeah, it's neat.
Cool.
I find this more satisfying than the discussion of the Lowenheim-Skolem theorem.
Yeah, and it's exactly the sort of the criticism I was making before about this, like practice of just like chucking in constants to like to enable the theory, the language, the first order language, to speak of the objects in the meta theory, is just like, yeah, I think that's wrong. Like it sort of it makes the story a bit more circular in terms of you're supposed to start with your language
Mm-hmm.
and then sort of make like relate it to your models, but then you're like throwing the model into the language. Yeah.
Cool. All right. Shall we leave it at that?
Yeah. Thanks for indulging me and letting me go over time.
No, not at all. Thanks a lot.